Hello, hello. This is a fun run. Let's see, where were we? Garbage. Oh, there was... what do I want? What was down here? There's something special. That's right. So we need an escape card, and we need brimstone, which is a big ask. But there's only 3 in this room. Alright, we want a card. That might work. No card yet. Alright. How's everybody doing today that's joining now? Hopefully my bot's actually right this time. Hey, good bot. Caffeine. Yes, that's what we want. Part 1 of making the dream. Now watch me not get the thing I need. Okay. Good. Are we too foolish? No. There. Alright. Double deal. I run. Yeah? Dream's still alive? Maybe? Money. Oh well. No instant run winner today, it seems. Unless if it's in here somehow, but I doubt that's going to be the case. Reverse amount or money. It's going to work? No, it doesn't work. What a waste. Bet the lasers are going to bounce off the walls. Very quickly. there. How's everybody doing at the lab? Hello. Hey, Philip.
家は前と違うけど、3学期だけこの学校。マジか。うん。まあ。久しぶりだな。かもね。引っ越して3年だっけ?
Hopefully we're not cursing in anime.
4年か。そう、4年。
Just the screen.
ピッチャー頼むわ。え？前はよくやったろ？前はね。遠慮すんなって。
Are we actually gonna make boss Rotational as the Lost? This is where a smarter person would bail out. You're right there. We've done it. Absolutely useless item. Alright, I suppose that means it's time for class. Harumph. Nothing we wanted out of there. How's everybody doing today? Oh. We've got a Philip. And hopefully other people too. Alright, enough Isaac for today. Or until after class. Doing good. It actually uses DirectX to implement WebGL instead of OpenGL. I got my during class snack. So Edge, that's, do you know why it does that? It seems like there's extra steps that don't need to be there. Did you bring enough snack for everybody? And is it pickle related, since you're an aquatic pickler? Well, Microsoft forked Google Chrome, or Chromium, didn't they, for their new version of Edge? Wasn't that the big thing that came out recently? So, yeah, whatever. Okay, fun stuff. Well, good to know. Yes, but it still uses DirectX. Oh, okay. No pickles today. The thing called Angel. Interesting. I did not know that. That's interesting info. Alrighty. Well, I suppose we can get going here. So I've got a couple of nifty things to show you. So one of them, so this is something new for you all. I'm prepping a cloud applications course for grad students, and I think I actually have a couple undergrads in there too. But I guess that's another point. If any of you are interested in the material, you can actually use your cloud credits that I've given you to do some of these nifty labs. But this one's pretty cool. So there is a thing in Google called Bigtable and BigQuery, which is basically their massive big data processing engine. And this particular lab we're going through, it's basically to demonstrate how to use Java to link up to this thing. But one of the people who created, did some work in here, he realized that the visualizer baked into this particular database engine can be coerced into making art, which is kind of interesting. So basically, this thing is on the left here, this is a visualizer for showing activity. So basically, it's a list of cells with things happening, and they're colored based on the activity level. So he took that and turned it into a artwork transformer type tool. I think it's kind of nifty. But yeah. Oh, yeah, here's some of the other stuff that you can do too. Basically, it starts off with like just ones and zeros and all that. Using BigQuery to try and find Bitcoin on GitHub repos. I can, since I think we've got a minute today, and if not, I'll just have to leave you one or two slides to read on your own. I find this thing fascinating. Let me pull up a quick slide really, really quickly here. So I did a demo for the GVSU faculty on cloud stuff, since that's one of my things. Where's my slides? Cloud Classroom. Okay. And I should mention too, so any of you that are interested in the cloud, your credits that I gave you for your websites, you can use them for anything in the cloud, as long as you turn it off when you're done. Big table demo. I didn't create a new project very quickly. But you can search through the entirety of GitHub in seconds. So I'm just going to grab this quick query, which is SQL-like. Let's pop over to BigQuery. And basically what I've got going on is with this thing, I create a brand new project for every demo, and then I delete it because otherwise all my resources get sucked down, which is bad, especially when you're running classes. If you make an Alexa skill, AWS gives you... Nice. Yeah, you can get free credits through Google too once you're like done with my class credits if you want. I know there are ways to do it. There's a free tier. There's you get like 300 bucks in free credits. I don't know if they have any incentives like that. But if you are interested in database stuff at all, they've made a ton of data sets public that are big data. Um, there's COVID data in here, there's census, there's genome data. So if you have any interest in like analytics of any kind, you can play around in here. But I find this query fascinating because, Google's BigQuery, it's not a SQL environment, it's a NoSQL thing. Basically, it's a massive sparse database, but their query language is very SQL-like, which is nice. And if any of you have ever played with any NoSQL databases, but they're not always easy to query. Like if you go the graph-based ones like Neo4j, they have their own language for getting data and all that. So this is nice. But this is going to parse through 23.5 gigs of data. And we're just going to select basically a sum, which is just going to add up all the instances that it finds of the GitHub repository data set where it finds fix me and to do. So basically, anytime these uh, lines of text are found in any GitHub repository anywhere. Syntax error inspected. That's weird. Okay, so it ran. I don't know why that error popped up, but this thing ran in 4 seconds, and we found 8.5 million records in GitHub where fix me and to do exist. I think stuff like this is just awesome. And any of you that are traditional database people, you've done MySQL or Maria or SQL server, if you parse through 24 gigs of data, that's not necessarily going to be quick without optimizations. And something similar would happen with petabytes of data. It will run a lot quicker. But then you get charged for the amount of data you're processing here too. I think stuff like that's fun. Anyway, let's talk class stuff, which is why you are all here. Not, okay, I know some of you have to be anime fans of some kind because I can't be the only one. Um, is this Akira or one of the older? It's one of the older animes. I can't place the characters. It's driving me nuts looking at this image here. Not relevant to class, I suppose. Cowboy, is it Cowboy Bebop? Oh God, if it is, I'm gonna feel really bad. I liked that one. I came up and I didn't get too into anime, but I was in college when Adult Swim used to run anime after midnight, and I just would stay up watching that. It's a lot of fun. Nice introduction. Okay, other demo. I know you love hearing about P5 by this point. I found another cool library. So I've got my webcam over here on my laptop. This is my fancy camera for class. This thing is an ASCII art generator. So this is happening in real time in P5. Basically, it's grabbing the camera feed and turning it into ASCII art. I think this is awesome. And I'm very, very, very surprised at how responsive it is, because P5 is not known to be fast. It's not known to be optimized. But this, I mean, it's a library on top of P5. Somebody wrote this specifically. But I think ASCII art's a lot of fun, and you all get exposed to that now too. Yeah, and if you click, here's the raw feed, and it shows drawing on top of it. But there is like a microsecond of a delay in the feed. So another nifty thing that you can do with that. Alrighty, let's talk perspective. So before we get into this, does anybody have any lab issues? Because I believe I have that set for tomorrow night being due. March 19th, which is tomorrow night. There was one, so one of you was having issues, and I'm wondering if other people are having that too, where if you start playing with the number of particles slider and you have the collisions dictionary implemented, make sure that you have that collisions dictionary grow to the correct number of particles, because otherwise you're going to start getting errors with attribute not found. It'll be dot length or dot something or collisions can't be found or something like that. I didn't explicitly put that in the lab manual. It's kind of why I'm bringing it up as a hint. But make sure you check that out. And if you haven't started the lab yet, today might be a good time to do that, because it's, to me, a little bit longer and more involved than the last one. Okay, so we ended about here last time, and we were talking about the different projections that we have, right? We have perspective, we have parallel projections, and one question for all of you to get this started. Why do we have all these different ways of viewing things? So why would I say choose an isometric view or choose a perspective view or a oblique view? What's the purpose for all this? Sorry, super dry in here today. So I'm not sure what the lag is like for you all. question posted to chat? I don't know. Hey, Tails, you're supposed to pop up. Why didn't you pop up? Who did it? Hmm. I know, but let's see if anybody else knows. Okay. I don't know if Tails popped up for all of you. He was supposed to pop up. Maybe he's behind. Let's try that. We'll try this again later. Um, so we have all these different views, right? And I started rambling on and on about the different ways we can draw them. We're going to get into how we basically form all of these today, but we need these to show different aspects of an image or aspects of a model. Basically, depending on which view you pick, you can get different information. Now, some of these you would use for architectural modeling, for, adding units to really show, how wide something is or how deep something is. Some of them are just for aesthetic views, right? Maybe you're making a game you like, the isometric style, where your axis is slightly tilted at more of an angle. Some of these are, again, great for architectural drawings where I can put this is, 10 feet to 10 feet. This thing here is 50 feet, whatever we need to show to the user. But at least from our perspective, in terms of WebGL, we don't necessarily care. I mean, we do care because we want to show the appropriate thing, but we're all going to represent these as just a matrix of information, and we're just going to feed that into our pipeline. It's going to be multiplied by the current transformation matrix, and we will get different view. Basically, we're just changing our frame of reference around. Now let's see if this comes back. There he is. Haha. Something I set up 2 years ago and I never really made a big deal about because it's hard for me to quickly notice tails popping up. All right. So we have different categories, right? And kind of the big distinction that we have is between parallel views and perspective views. And what this basically means is that we are going to be preserving scale, for instance, in parallel. We're going to be maybe preserving units of measure in some. It just kind of depends on what we're trying to get at. But for categorizing them, we have parallel and perspective. Parallel, you have your multi-view orthographics. We have our obliques, which oblique is kind of like these guys here. We have our isometric views, and these ones we'll get into what they all mean. We also have perspective, where we have like 1-point perspective is this guy, 3-point is this guy. We've got a couple more examples of those as well in a moment. But based on how you categorize them, it kind of really, helps you plan what your application is going to look like and how you form that matrix. So, big difference is perspective or parallel. That's basically question one you want to answer if you are choosing a view. So, what does perspective mean? Well, basically, I guess I should step back a little bit. Regardless of these views, the goal is to transpose a 3D object onto a 2D plane, right? I've got my window here, and I'm just kind of circling around your monitor, right? Or your video if you're watching this later. And this screen, or it would be a piece of paper if you're drawing, whatever you're doing, it's taking the 3D image of me that the camera's recording, transposing it into a 2D flat space. We have the illusion of 3D because of shading and distance and all that fun stuff. But that's what we're doing with projection, projecting onto a screen. Now, in perspective, what we typically have is a center of projection, which is typically going to be like your eye or the camera lens or something like that. Basically, it's where we are starting to look at. At the other end, we have the object, and somewhere in between is the projection that is happening. Now, if you remember when we talked about the clipping plane or the clipping volume, depending if we're in 2D or 3D, that point in between is where we show stuff. right? Anything outside of that we hide or we cull. Inside we show, and that's a cube. It's at the midpoint of our pipeline, and it gets flattened down into a 2D object later on. But based on how we draw basically our lines of projection is how it's going to look on the 2D surface. So here you see we have basically like rays going out to the different corners of this cube. And based on how we hit the projection plane, that's where we draw the vertices. And this is going to happen fairly seamlessly for you in the WebGL world and Unity and all that fun stuff. Parallel, we don't have a center of projection. We have degrees of projection, or direction of projection, sorry. We see these lines coming off of a face in parallel, right? That's why we're getting parallel from. And that is going to inform what our rendered projection looks like. So if you need to know the TLDR, or too long didn't listen, too annoying to listen to didn't listen. Perspective, we have a center of projection. Parallel, we have direction of projection. So parallel lines coming off of faces with parallel. Projector, one central point emanating lines towards our corners there. So that's our differences for that. So our first view is orthographic, which, spoiler, this is our default view in WebGL, is orthographic. If we go back to our category, orthographic is going to be a parallel projection. So that's where we're starting here. And you can see that in these parallel lines coming off of the face of this particular object. And I keep saying face. Basically, that is just, this is a face here. Is this going to work? Okay, that works. So this is a face. This is a face. Like the top could be a face, depending on how the object is oriented. But based on whatever face we're showing to the camera, we're going to get parallel lines coming directly off of that. And it's going to come basically at a perpendicular angle. Now, what does orthographic mean? It is at right angles, is what that means. Okay, so multi-view orthographic. We have different faces that we can be showing to our viewer or our camera. And what this means is that our projection plane is going to be parallel to the face that we are looking at. You probably have seen this if you've done CAD. I know we talked about this in the past being 2 days ago. It was such a long time ago. But we have our three principal faces, the front view, the side view, the top view. These are your multi-view orthographic projections. If it is a top view, it is a top orthographic projection. If it is a side, it is a side orthographic. Multi-view, we get multiple views. And typically, if you were to do, say, a CAD application, right, if you were, say for your term project, you decided you want to do AutoCAD for the browser, you would have a way to render something like this out. So somebody drops a Blender model into your application, you generate an isometric view, which is what we put in the top corner here. I should mention and be very clear, isometric is not orthographic, or it's not multi-view orthographic. It is just for viewing purposes. But I could say swing the camera around, here's the front. Swing the camera around, here's the side. Swing it up, here's the top. Okay, we get our different views. And what we project to the camera is basically what you see. Hopefully makes perfect sense to you all. Now, multi-view orthographic, why do we like this? I'm going to have advantages and disadvantages slides for all of these. So if you want to know why you would pick one over the other, here's kind of your rule of thumb. Now, with multi-view orthographic, it's going to preserve distances, it is going to preserve angles, meaning that this thing is absolutely wonderful for CAD drawings and architectural drawings. Preserving angles and preserving distances. I can put exactly how long a surface is, how tall it is, at what angle the corner comes up off of your building, right? This is all perfectly preserved. We are not getting any distortion. So, great for CAD. That's why those of you that said you took CAD in high school very, hopefully fondly, remember this, because we have great, abilities to write plans. But you don't really see any hidden surfaces. So let's say that this particular object, maybe there's a wall here, like a solid surface, right? It's not pillars. And those of you that are taking history, hopefully you get the Corinthian pillars or I don't remember my pillars. It's been a hot minute since I took world history. Dorian, no, that Dorian's a guitar scale or mode. But if we had surfaces here, we couldn't see inside the building. We'd have to either make it transparent or pick a different view. Isometric is why we add that in so we can kind of see hidden surfaces. We can see extra detail when we're building things. So that's why you typically toss an isometric on there. So multi-view or multi-view orthographic. Next one up is our exonometric. And this one falls into parallel as well. Now, exonometric, we have isometric, dimetric, trimetric. Isometric view is the one that we have been talking about so far. All that means is how many angles do we have that are identical. So here we see this kind of theta 1, theta 2, theta 3. We're just looking at this corner, right? And we are saying, what is the angle of this thing? So once we project it, are these angles between our different planes or our different faces identical or not? And if we have 3 identical angles, like you see here, this is probably a 90-degree angle we've got. Or no, not 90. What am I thinking? Greater than 90. If we have 3 that are the same, it's isometric. If we have 2, it's dimetric. If we have none, it's trimetric. So basically, these angles, we can figure out how many are identical. So here we have, this one looks like it's a 135. This one looks like it's a 135. This one looks like it's a 90. So we would have, oh, this should be isometric based on this figure. Maybe it is 135 and I'm just kind of looking at it funny. But kind of the key is, what are these angles between our different planes or different surfaces? And the orientation does not matter. As long as it's with respect to the object, it should be able to be categorized as such. To give you a better view of what this looks like, so here's our isometric view. If you take that figure that we had before and kind of transpose it, we'd be looking at our principal faces here. So here's the down aspect. This could be going off and say y or x and y and then z. Here's our trimetric. None of these angles are identical. Dimetric, we have 2 that are identical. So we've got, let me get my laser pointer back. Okay, it worked the last time. So if we have an imaginary angle here, okay, and one here, these 2 are the same, but this one is way bigger. So it'd be dimetric. Again, it's just important to note that these are all classical viewing angles. And if you're going through art theory or architecture design or anything like that, you would get a ton of details on these different views and it'd be a lot of class time. These are just, again, going to be matrices that we fill in. Now, the differences between all these guys, why you would pick one over the other, again, hidden layers that we can see more of, or hidden surfaces. So if you look at dimetric, it kind of looks like we just have one set of pillars, right? Now we have 4 here, and then we have another 5 going this way. You don't see any of the ones in the back. Trimetric, we can kind of see them going off here. Isometric, we get a little bit of a different perspective as well. I don't know that we can see more in this one or not, but based on how you angle things, you can basically get more detail. Consider this akin to opening up Blender. You render your beautiful image, and then you start swinging the camera around or swinging the orientation around to make sure that you cut everything, that you have it set up properly. So, different views. Ups and downs for this guy. Now, here, the lines are foreshortened, meaning they are scaled. So we don't necessarily have a one-to-one exact measure here, right? This particular length is identical to this length in reality, but they look wildly different when they're rendered. But you can calculate a scaling factor, meaning that we can, go from one to the other with basically a multiplier. Angles are not preserved here as well, so with our face angles kind of being either 3 identical, 2 identical, none identical, all the angles are going to be different. Again, we can calculate them out though if we need them. So, example, if you're in a project circle on a plane, but it's not parallel to your projection plane, you end up with an ellipse. So basically, I have a circle, I try to project it, it gets squished. Our angles are not preserved. But the upside, we can see 3 principal faces, meaning we can see a lot of detail. However, we can get optical illusions, and this is, again, a result of foreshortening of angles not being preserved. Basically, we can start seeing weird things happen. We might get the fact that our parallel lines in our projection direction of projection, they might not appear to be actually parallel, even though they are. This is where you start looking off into like the distance of a model. Might start looking funny. And we might not have any reality. Things might not look real. They're going to look weird. But that's what we get for being able to see more. Right, so here I can see 3 principal faces. Here's the front, the side, the top. I can see all of that. We can accept optical illusions for additional information. And again, if this is all we have, we can use scaling factors to get back to the real values. Make sense so far? Again, these are used in CAD applications. Computer-aided drafting, if you're not familiar, like AutoCAD, like SolidWorks, like any of the other ones that are out there, Google SketchUp. Basically, these are useful. Okay. Ooh, down to 5 viewers, even though I see like 10 of you in the list. So Streamlabs' ability to keep up with who's in chat is not the best. Alrighty, so pros and cons set. We also have Oblique, where we kind of have an arbitrary relationship. I'm really trying not to read the slide to you because otherwise I just give you the slides and say, here, go read it. When we say arbitrary relationship, basically we can kind of move things around to get different perspectives, if that makes sense. So before we have like a center of projection and we are emanating from that and then we're getting our image on a surface, or we have these parallel lines. Here we can kind of move the plane around, we can move the object around, and then we get this oblique view. All right, so here we see basically we have this object. It's projecting down onto a plane. Here we have I think this was the elevation oblique. Here we have a projection plane that's actually higher up than the image, so we're going to kind of get a skewed view of things. We do have parallel lines coming off of it, so that is one key. Right, if we go back a few to our categories, oblique is technically a parallel projection. So the projection lines, are coming off in parallel. Again, they don't necessarily look parallel here, but here and here they're very clearly parallel. This allows you to get kind of it's going to look like a very weird view if you actually look at the object, but you get more information that you can see. All right, and this is a very common thing that we do. Maybe you want to emphasize a particular face or set of faces. So we had plan and elevation oblique, right? Do you look at the top or do you look at the front and then swing it around? It's kind of your standard, let's draw a cube by hand kind of view for if you were to sit like and sketch something out on paper or on a whiteboard. This is my cube. It's probably going to be an oblique-ish type of thing. but this is not a image that we can actually create in real life easily. Basically what happens is that we have some face that is fixed, and then we kind of swing our camera around to get more details. Now, if you wanted to take a picture like this with a camera, or well, let's take a normal camera, for example. I take a picture of a cube, it's not necessarily going to look like this. Um, I would have to take the picture of the front and then swing the camera around to get more detail. Now, this is possible with something called a bellows camera, which is an old-timey camera. Bellows camera. It's one of these types of deals where we basically have some flexibility with rendering our image, basically. Rendering our image, taking the picture. Okay. Control Shift F. Does that work if I do this? Escape? Yeah. These key bindings are hot garbage. There we go. All right, so basically, let's see. So these are all the parallel views that we're really going to talk about. Let me go back to our categories here. So we have our multi-view orthographic. We have our exonometric, which is your isometric, diametric, trimetric, which just means what is the angle between the faces. Figure that out. We have oblique, where we basically fix a face, and then we're going to show additional information. Again, here is our oblique types of views where we really are focusing on one face, but then we're also moving our image around a little bit to get some extra information. Everybody good so far? Those are our parallel views. On my daily realization, I forgot to hit record, so you get the Twitch stream pull down later on. Yep, okay. Thank you, Philip. Okay, so interestingly, I've already mentioned this. We don't necessarily have a lot of hard work to do for setting a view up in WebGL. We're going to pick the view, we're going to fill in the appropriate matrix, and we're going to go from there. If we are doing an oblique angle, we're actually going to make use of shearing, which we'll talk about a little bit later on, meaning that our view matrix is going to have a cotangent in it. So we'll kind of get to that. Now, one of your other issues too is that we aren't necessarily, we're more or less approximating these views. So there can be a little bit of a fudging factor that we have to add in to make them perfectly that projection, basically. So we'll come back to that. All right, perspective. Now, with a perspective, we have a center of projection, right? And this was the thing that I mentioned before. Here we have a person with 3 lasers shooting out of his eyeball, and we are projecting onto some surface. So in reality, this is you. For graphics applications, we have a simulated camera looking at some object, and wherever we have the projection plane in between that center and the object is what we're going to see. This is that thing where I told you before that the farther away something gets, the smaller it looks, right? Did my Kirby example, pull them farther away, I can kind of get a, that kind of a thing going on. This is just a result of the fact that we have angles emanating from the center of projection, and based on how it gets projected to the surface, it's going to look bigger, it's going to look smaller. Parallel doesn't have this issue, but we can get optical illusions with parallel. So with this, we have to talk about the notion of a vanishing point. So a vanishing point is what we get in perspective by having some imaginary point off in space and all of the angle, or sorry, all of the lines coming off of our object converge to that point. So think of it like a reverse center of projection in a way, where here we have a cube where it's got a vanishing point, say right here. We're going to draw invisible lines off of it towards that point. Now, this is a perfectly set up cube, or a rectangular prism, since maybe it's not an exact cube. But if you're looking at this purely to get angles or lengths, you're not going to get the correct value. Right here we have a very acute angle. Here we have a nice oblique angle. In reality, these are actually 90 degrees because it's a perfect rectangular object. But because we have this vanishing point here, we're basically drawing the sides heading towards that thing, right? This vanishing point. This is going to give us a perspective. Now, it's something that's going to be helpful to visualize this because we have three different perspectives that we can use, is how many vanishing points we have. So if we have a 1-point perspective, we have one vanishing point. All lines emanating from our surface go towards that. Right, so we have one basically primary face that we're looking at, and it's gonna the back side of it's gonna shoot off towards some vanishing point. With a 2-point perspective, we're gonna pick two faces, and we're gonna send off our invisible projection lines towards this vanishing point. With a 3-point, you're gonna pick three faces. Hopefully this makes sense. Again, with all of these, we're just going to get different perspectives of our object. And I shouldn't use the word perspective when I'm talking about perspective, but that's what we're really doing here, right? How are we representing this object? How are we kind of scaling and mucking about with angles and squishing and pulling this thing apart just based on these random points in space? That's what our different perspectives give us. So I've got a few figures here where I've kind of drawn lines over them. I don't have them necessarily converging, but you can hopefully kind of see the angle that we're getting towards. So with our 3-point perspective, basically we have three vanishing points and our lines are going to converge to that point. All right, so if we look at this object here, 3-point perspective, you see lines going this way, lines going this way, lines going this way. So we're kind of, again, showing a different visual for the object, right? And here we could see lines going this way, we can see lines going this way, we can see lines going down this way, and that informs how skewed our object actually looks when it's projected. 2-point, same idea, except we just have two vanishing points. Here we're gonna go probably to about, looks like here, so right about here. And then our other one, we're gonna go off in this direction, right? And we're going to materialize over here. Now, since we have a 3D object, we probably have one line back here, which again brings us into 3D space. I only drew two lines, but really we have 3 dimensions to deal with, so we'd have more than one or more than two. But we have some line or some point out in space. That gives us our perspective. 1-point, same thing, except we just have one vanishing point. Great for showing one principal face. Here we can see two principal faces really well. Here's our front, here's our side. Here we get three faces. Face number 1, face number 2, face number 3, the top. So side, front, top. Are they perfect? In terms of recreating a real world object, no, things are going to look distorted. We have a non-uniform foreshortening, meaning that our lines that we are drawing are going to be different lengths, and it's not necessarily easy to recreate them. Right? We don't have a singular formula to say, get our correct scales. It is not uniform. We do preserve angles, which is good, but only in the plane parallel to the projection. So here, these angles are perfect because this is parallel to our projection. Other angles on the other faces, not preserved. So what are we getting here? We are getting a view which is not great for CAD-based applications but we can get a lot of detail visually and we can see what is going on. You know, we can see hidden surfaces, we can see better depth. This is also a little bit trickier to draw by hand too. So if I were to sit you all down with a piece of paper and I would have you draw a parallel view and a perspective view, the perspective would be a little trickier because it's going to, again, that whole non-uniformity is going to make life a little bit more difficult. I'm not saying it's impossible. I'm sure you could all figure it out. But it's just a little bit trickier, and there's some extra gotchas that you have to work with. But the computer is going to be fine. Again, it's going to be a matrix that we build for it. Okay, any questions at all? That is our perspective overview. Got about a half hour left, so we'll start talking about matrices now, and I'll try to make sure that you all stay awake for that. All right. So, camera. This is finally the fun part. And then we're going to talk about the camera, and then we're going to be done pretty much with WebGL after today. So, our camera is going to be our center of projection for all of our perspective views. And it would factor into parallel as well. But it is just some invisible object that we have in WebGL, or in OpenGL, or SDL, or Pygame, or Unity, or whatever engine you're using. It will have a camera. Whether they talk about it or not is one thing. But for WebGL, at least, we have to position this thing. 3 aspects to consider. Position the camera. If you remember, sorry, hearing kids screaming, I'm guessing, I'm sure that's fine. If you remember back to when we talked about our pipeline and our current transformation matrix, one step was the model view matrix. This is how we can position our camera, is by setting it appropriately at the model view matrix stage. Let me pop over to some code here. Oops, gotta make that bigger. 14, 24, please, thank you. If we look at ortho, because we're gonna have to come to this one anyway later, and we look at our shader, we're going to see the position times model view times projection. Every shader from here on out in the book, or in the GitHub page that I took from the book, is going to have something that looks like this. This is our building up our current transformation matrix, model view matrix, projection matrix. These are what we are setting right now. Excuse me. So, if we are going to set our camera, it's the model view matrix. If we are going to pick a camera lens, it's the projection matrix. So going back, set our camera position, pick our camera lens. That's how we liken it to real life here. Third, let's clip out what we don't need. We can set our view volume. In WebGL, we have a default cube of space that we are looking at. We can update that if we want the clipping volume to be larger or smaller. That's something that we can tweak as well. So here we get some technical stuff about WebGL, the moment you have all been waiting for with bated breath, I'm sure. Object frames, camera frames are identical initially. So everything we have done so far, camera, object views, have been the same. Our default model view matrix, so this particular setup here, has been an identity matrix, meaning that there is a string of ones running down the diagonal, everything else is zeros, and if you multiply anything by that, you get what you already had, right? It's an identity, meaning that we are not changing anything. WebGL, our camera is started at the origin and it's pointing in the negative Z direction. So every time I've told you, if you want things to kind of go off into the distance, it's going in the negative Z, not the positive Z, as you might expect. So we also get a default view volume where we have a cube whose sides are length of 2. And you should probably realize this already because we're on a range of -1 to +1, meaning that we have a length of 2. If you add this together, right? Centered at the origin, Default projection matrix is also an identity. Again, because we haven't really been doing anything with our camera, we haven't had to mess with this at all, but it is an identity. Our default projection in WebGL is orthogonal, so parallel. And these pictures are going to start to kind of look a little bit wonky. I'll do my best to try and explain them as we go. This solid rectangle here, this is our projection plane. So this is what your screen looks like, or your browser's canvas is, basically. This blue cube here is our clipping volume. So this is our length 2 cube that we have. Here's our origin, here's our frame, and anything outside of this clipping volume, or this view volume, is clipped out, meaning we don't see it. So if you see these arrows here, basically it's just saying anything in this volume gets displayed on the projection plane. All right. Hopefully makes sense. And we see parallel lines of projection coming off of this clipping volume. Now, maybe we don't want that. Maybe we want to move our camera around. Let's say that we want to move my Kirby, because he's handy. Link's all the way off in the distance. Oh, that's perfect. Link's in the distance, Kirby's right here. If I want Kirby to go back to Link, I could move the camera, or I could move Kirby. Right? One of you asked, I think, 4 or 5 classes ago, do you move the ground or do you move the character? And I would say, it's up to you. We can move the camera, we can move the objects. Again, it's just a transformation that you apply. And if you're applying it to the object, then it's a transformation or a translation for the object. You can do it to the camera, meaning you just move the camera around. Now, if we want to move the camera, we would just translate the camera frame. If you want to move the object, move the world frame, which has all the objects in it. Now, I could move the camera in the positive direction. I'm not going to touch my camera because I'm afraid it's going to break something, but I would say we start here, and I pull Kirby back. Here, we're moving the world frame around. If I were to move the camera, let's pretend I'm grabbing the camera here, and Kirby moves back. I'm sliding the camera in positive, meaning it's moving farther away. Kirby stays the same. Or I move Kirby in the negative Z, camera stays the same. Hopefully not too hard to wrap your heads around. Basically, just think of taking your camera and physically moving it backwards. That means we're moving it in the positive direction because we're pointing negative, right? If we look at this particular figure here, XYZ, here we have our camera, say, positioned right here. Let's say this is Z of -2, or sorry, Z of +2. We are looking in the negative direction. Okay? So if I want to move backwards and I want my objects to get smaller, camera has to move this way, meaning it moves positive Z. If I want the objects to get farther away, I can move the world frame this way, in the negative direction. For us, we don't care, right? It's going to be the same thing. We're going to just apply it to the model view matrix. And if we want to generate that matrix, we could either construct it by hand like you all did with those map4s, right? And you move things around in the negative or positive direction by filling in the correct axis, when you're moving your triangles around and things like that. We can also construct these in JavaScript with our library with the call to translate. So 0, 0, -d. This is going to create a 4x4 matrix that we can just send to our shader. To give you the visual here, and we're not going to get through all this today. I thought we would, but I guess I'm being overly talky today. By default, this is what we have in WebGL. Here, if we move our frame by -d, we have shifted our frame this way. And again, every object technically can have a frame. Our camera has a frame, our world has a frame. Objects that are instants inside that frame have their own frame. And this is just matrix math that we're going to be working with here. So if we want to move the camera around, let's say we want to rotate it and move it away from the origin, what do? Well, here we have our nice 1800s era camera. we start at the origin, right? So this is where we begin. First thing we're going to do is rotate it. So let's swing the camera around. We're going to apply a rotational matrix to it, and then we're going to translate it, meaning we're going to move it this way. And don't forget that we are post-multiplying here as well. So the first thing you want to happen has to be at the end of the list of operations. Right, that's just how matrix math works here. So our current transformation matrix for this particular activity, C equals TR. Again, fill in T, fill in R with what you need. Either do it by hand with the mat4, or use our library call to translate, call to rotate. Actually, I've got the code for you here, which is even better. I forgot I had the slide here. So if I want to generate these matrices, this would be my current transformation matrix. Say M. Say var t equals translate. Move in the negative d direction. We're going to assume d has been defined somewhere else. Could be like 1, so let's move it in the negative 1. We're pulling it back an entire unit. Let's rotate about y. So we have our x, we have our y. So we want this thing to kind of swing around this way. Right, so we're kind of angling like that. And then let's multiply them together. You can concatenate them all into one line as well. You don't have to do separate variables. You can, if you want to, say, log your variables to make sure everything is being constructed correctly, but nothing wrong with doing it all at once. Just keep in mind, rightmost first. Make sense so far? Again, I can show you ortho.html in chapter 4. So, okay, thanks, Phil. It's nice. I don't want to hold you all to interacting with me because I know you don't necessarily have to right now, but it is nice when people say that they're here. Otherwise, I'm talking to video. Chapter 5, ortho.html. So if you... Does JS mean JavaScript? Yes. Yes, it does. So go to the Git sites, chapter 5, orthogonal. These buttons aren't going to do too much until we really start talking about it. But this is this is an orthographic view. Kind of see weird things going on with the clipping plane here. But basically, this is a good start to looking at the various matrices. We're not going to talk about hat and hat A, but these are fun ones too. So this actually would have been better to talk about when we were talking about modeling. But this figure that you're looking at here, this is actually a well-known hat function. Let's try to move you back and change our clipping plane. Yeah, no, that's fine. If you want to double check, I'm more than happy answering that. But ortho.js all the way over here for some reason. We can define our matrices in JavaScript. So our model view matrix, our projection matrix, and we can create them in here. Where's my creation? Yeah. So our projection matrix can be orthographic. Our model view matrix, we're going to talk about look at here really, really quickly. Basically, we're taking all of the effort out of constructing the matrices, and we're using these API calls. And get comfortable doing stuff like this because this is what pretty much every library is going to have you do. Now, yes, you may have to construct pieces of it. Like for generating a camera lens, we need a radius times the sine, radius times cosine, to populate these things, but we are still getting a nice 4D matrix out of these API calls. So this code, yeah, we're going to generate translation matrix, rotational matrix, multiply them together, send it to our shader, do our matrix math, and then we have our 3D object. Okay, so first things first, we can do that. Highly recommend playing around with ortho, by the way. Look at is the next API call that we're going to be checking out. Now this is effectively a nice helper function for you to figure out what the camera is looking at. So think of any time, I'm going to guess some of you have tried making games at this point. You probably have had to deal with the camera. Like if we take our Kirby here, and he's walking along, now he goes out of frame. Oh crap, what do we do? Camera's not looking at him. Well, the camera has to follow Kirby along, right? So if he's kind of hopping along, maybe you're sliding the ground under him, or you're moving Kirby and you're moving the camera with it. But it's important to tell the camera what to look at too. So if we are, let me clarify because I just realized I said something kind of dumb because it's not what's on the slide here. If we are having the camera follow Kirby along, we're translating it. Right? So we're basically doing what we did here, just kind of move it along in, say, the x-axis. But this would be more like if Kirby's down here and he's facing this way, we could swing the camera around and have it look at Kirby. Okay, so let's angle this lens. And what we need here are three three-dimensional vectors. So we need the eye location, so the eye's x, y, and z right here. So this is your center of projection, if you recall. We need the place that we're looking at. So basically, we're going to calculate a vector from here to here. This is how we're going to have our camera kind of like look at stuff, right? So we're going to do something like this. We move the look at function. But we also need an up. Anybody know what this might be for? Let's say we have a camera. Camera's center of projection is right here. This is its eye. Kirby right here is what we're looking at. What is up? Any thoughts? Because this is where I'm just trying to see if you're thinking about what we have going on here. I'm like the guy from Hitchhiker's Guide to the Galaxy. Got my second head. Perpendicular to the camera, absolutely. So, if I have my camera and I have my object, and I do this to my object, camera doesn't know any different. Think of it as an extra degree of freedom for the camera. If I specify the correct orientation, now I have every dimension that I need to basically render an image appropriately. Because if I give it a location and something to look at, this is all identical to the camera until we say this way is up. So you need that up vector. And if we look here at ortho, up is actually going to be, oops, a constant, as is at. Excuse me. So what is up? 0, 1, 0. Apparently T is making me burpy. So what does up mean? If I have let's pretend Kirby's our camera now. X 0, Y is positive 1. So that means our normal coming off of the camera is in this direction. I could have Kirby rotate like this and there'd be Y equals -1. That's my up if I want it to be like that. To maybe help understand if you don't quite get this, think of like yourself in an airplane and you're kind of doing barrel rolls. You need to know which direction is up to, reorient yourself to the ground, right? Because if you're rotating, your X is staying constant, your Y is flipping around, your Z is staying constant. So you need that extra degree of freedom. And the other aspect here too, at we also have made constant because we were just looking at one particular spot. We could change at to be farther off in the distance or closer. It doesn't really matter, but in this case, things aren't moving yet. So look at, helpful function. And if we look at the bottom of ortho here, this is basically being set every render cycle. So figure out, oh man, excuse me. I was recording right before class, and I think I've blown my voice out for today. Figure out what our eye is currently based on one of the parameters. figure out what we're looking at, pick the orthographic projection, and then we're going to ship those off to our shader. So it's going to end up looking like that. Oops, that got auto-corrected. If you're coming from OpenGL, probably DirectX has something similar. There's the GLU lookat function. Regardless of library, we're forming the model view matrix here. Whatever you need to do to get to that point. So set your I, set your at, set your up, and then just call lookat and plug those values in. Three-dimensional vectors. If you wanted an isometric view of a cube aligned with its axes, your I, let's put it at 1, 1, 1. So meaning that we are over 1, up 1, positive z, meaning we're further back. We're looking at the origin. So let me grab Link can be my camera. No, Link can be my object. Kirby can be my camera. I swear I'm not going completely insane yet. All right, Link is my object at the origin. Kirby, we're going to set x1, y1, z1. He is looking at the origin, and his up is like this, basically. So we know what the up is. Okay. And in this particular view, I guess it'd probably be isometric. He'd be kind of like that, because we get an angle. But we're just moving things around. Again, these are just matrices. What are we going to get through here? So yeah, we can play around with ortho, and then that might be enough for today. We'll see. So we don't necessarily just need to do standard XYZ planes. Based on what we want, we can position the camera with whichever angles and directions we use. This lookat function is non-standard. It is a helper function provided by the library from the book. If you look at 3.js or Babylon.js or Unity or any of the other frameworks, they will probably have a similar function, but it's not standard. Maybe you want to use yaw, pitch, and roll. Right? You want different angles. If you want elevation, azimuth, and twist, so it's something like this, where our azimuth is kind of the angle from, between X and Y. Elevation is the angle between X and Z. Twist is the rotation around the normal coming off of that. We could use a function like that as well, or we could model that as well. If you're going that route, you'd be doing your angles in polar coordinates. And it would then be up to you to construct the matrices that represent that particular view. Again, it just kind of depends on your perspective. If you're going yaw, pitch, and roll, that's going to be something related to the center of mass of your object. Like if you're an airline or a pilot, you're probably doing everything in yaw, pitch, and roll. Or roll, pitch, and yaw, I think is the correct order of that. Basically, the point is I'm just trying to get at these are helper functions, but they're still constructing these matrices, and you can use whichever coordinate system you want. It's completely definable by you. All right, so let's take a look at ortho a bit more. So this is hat. Let's look at ortho. So here we have our cube and our default view. Now remember, our default view is orthographic. It's an identity. We have all these variables that we are kind of playing around with. We have z, we have r, we have theta, and we have phi. All right, and these are going to inform the matrices that we create. So first, let's take a look at, swing you around over here as I get too much junk open. Up. So our shader for our vertex, again, these are these matrix multipliers going on. Fragment shader, nothing interesting. That's pretty much it for ortho, or the HTML page. JavaScript, though, we have our radius, we have our theta, we have our phi, and then z and r. I'm trying to remember where those guys were. Give me 1 second. Near, okay, so near and far. So z is near, r is far, which is something that we're going to be getting into a little bit further on. Um, Basically, we're going to calculate view volumes so we can change our clipping plane. That's what Z and R are doing here. But theta and phi, let's take a quick look at here. So theta, we actually have defined. So theta, I just want to show you where it's going in to the functions here. Up, up. So they're both going into the eye of the camera. All right, so phi is our x, theta is our y, phi is our z. This left, right, bottom, y top, near, far. Near and far are the z and r's. They're increasing and decreasing that view volume. Basically, by defining this particular matrix, we're changing our clipping plane. So as we dink around with this, if I increase phi, now we kind of see it spinning around the x-axis. Or sorry, we're spinning around the y-axis. Theta kind of looks like we're spinning around the x-axis. You can get some really funky behaviors going on here. If I increase z, I'm making my viewing volume bigger. Make r smaller. I'm just trying to get everything in order. I probably need to really update this demo with the actual values because it's kind of hard to visualize what's going on. Or maybe sliders would be better than buttons. But you can kind of see that by playing around with this top layer, we're messing around with their view volume. Our bottom layer, we're actually changing the eye of the camera. Now, what is actually happening here? Because this is an interesting thing to talk about. Is our object moving? No, our object is not moving. The camera's moving. Again, this is solely how we construct the eye of our camera. And what is our model view matrix? It's basically a concatenation of our world frames and our camera frame. And we're just shipping that off to our shader. Now there are other examples in here too. Oh, this one had the sliders. Okay. So Ortho 2 has actual sliders. And there's some extra ones. We got width and height in here too. But kind of fun to play with. Right, so we have that. Now, this is probably going to be enough for today, I think. Yeah. My guess is we'll get into all that next time. So that was all, that was all parallel. That was all perspective. Yeah, losing my train of thought. Now we're going to move on to parallel. So, questions at all from today, or any questions on the lab? Because that's, again, due tomorrow night if you missed the first 5 minutes of class. Nope. Okay. So one thing that you're going to want to do in the near future is install Blender. Because once we get through this set of slides, which will be Tuesday, it's looking like, because we are on slide 69 of 100. So I've got a little bit more on this and then we'll be done with it. Because basically it's about the rest of this fun stuff. We're going to go into Blender a bit, and then we're going to go into other libraries. I already have it from a previous failed attempt. Perfect. Yeah, so I'm gonna try to figure out which order I want to do it because I always waffle. Do we do Blender first and then the libraries, or the libraries and then Blender? But Blender is going to be the next thing that we do outside of WebGL. And after that, we're going to do Unity. So those are the two things to work on getting installed on your computers. And depending on when you installed Blender, it's possible they have a new version. Um, I think we're at least up a major revision since when I ran this class last, so I'm hoping all of my demos still work as I think they do. Oh yeah, a month ago you should be fine. Last time I ran this class was winter of 2020, so we've gone through a major Blender version since then. But yeah, your next lab is on Blender, so probably want to get that up and going. Let's see, Blender. Yeah. So actually kind of the fun thing though, since we have a couple minutes, let me set the tone for this. We're going to do a little bit of Blender modeling, and you're going to take what you render in Blender, and we're going to apply it to what we do in Unity. So we'll do a little bit of modeling, we're going to export it, and then you're going to make a little environment for your characters to run around in when we get to Unity. So other than that, I hope you all have a wonderful weekend. We'll end a couple minutes early here since getting into the next set would be probably a long discussion. So hope you all have a great weekend. I will see you on Tuesday. Let's get some waves going. Dark synth. Ooh, little blood sport action. Perfect. All right. Bye, everybody.